So next 20 minutes what I'll just give you about brief research work, what we are doing in our group, and followed by I'll talk about this particularly what do we mean by the soft material, and then couple of examples of that how you can use for the different application in the context of current energy and environment. Okay, so in my group we do research on particularly the functional metal organic framework, which is the porous material, and based on the design and principle of the organic ligand, and you have a periodic table multiple meta-ions, you can form the self-assembly and you can tune the pore size as well as the pore surface, and that material you can use for the different application, particular energy storage, harvesting, CO2 capture and separation, and different other properties. So then we also do that mix or the composite material based on this MOF or any other material like let's say graphene or amino clay. So where you can get that 1 + 1 is not equal to 2, you can get the 1 + 1 is equals to 11. You can get not only the new properties, you can get that advanced and enhanced properties of such material. We also do such kind of this organic porous material or porous polymers where there is no role of the metal ion, which forms by the CC coupling reactions between the different kind of organic molecules, like we do like Sonagasira coupling or Suzuki coupling, different type of reactions. You can get like this organic porous polymers where there the different chromophoric units you can introduce and you can do the different properties. So one of the disadvantages of these materials are the processability, because in the bulk state you have the low processability of this material, and where this is their application is limited in the several field. So then we came out that whether you can this kind of organic linkers, whether you can use as the low molecular gelator and you can self-assemble with the metal ion, you can get the salt processable material, which I'm going to talk today. So before that, for this audience, so what is gel? So gel is a viscoelastic material which contains two coexisting phase, a large amount of the liquid and a solid network which immobilize the flow of liquid. Okay, so classification of gel, if the solvent is if the water is the organic or water is the solvent, you will get the hydrogel, and if the liquid phase is the different type of organic solvent, you will get the organogel. But the gelator, which is already a polymeric gelator oil exploited, and you have the low molecular gelator, which through self-assembly, different type of non-covalent interaction, it forms the gel. And metallogelator, discrete metal complex, which can also act as the gelator and form the gel. But when you have the low molecular gelator and you self-assemble with the metal ion, you will get the coordination polymer gel. So these are the different of supramolecular interaction where it forms in the molecular, in the isotopic state, isotopic solution. In anisotropic self-assembly, like it can form the fibril, and this fibril through interconnected or interdigitated, where this forms the three-dimensional network where solvent molecules are entrapped and it can form the gel. So why to introduce the metal ion? So when you introduce the metal ion in such kind of through the self-assembly process, you can get the unique redox, optical and electronic properties of the metal ion. You can introduce to the metal ion. You can tune the morphology of the systems by binding the metal ion. You can get the high processability of the CPG using different application. So you can get the tunable emission, drug delivery, catalysis, gas storage, sensing, self-healing and stimuli responsive properties. You can introduce such kind of hybrid system. So I'll give you a couple of examples. This is our design approach. So what we do, we take the different aromatic core. These are the aromatic core. This aromatic core you can tune or you can functionalize to the system. So this aromatic core, you can connect such kind of alkyl amide chain through this, which will give the flexibility, as well as the amide group, it will give the hydrogen bonding interaction. So now you have the metal binding site. So this, when you change the different chromophore, you can introduce the different type of functionality into a system. So not only that, metal binding site, not only this is the chromophore, metal binding sites, particularly your terpyridine, to that your different positions of the nitrogen group, phosphonate, sulfonate, and the carboxylate group you can introduce, and according to the metal affinity to the particular metal atom, like let's say that we have oxygen group, if you introduce, the oxygen group will be highly oxophylates for the lanthanide metal ions. So that way you can self-assemble such system. So first let's give this just one example, how the synergistically that if you connect this kind of low molecular gelator with the metal ion, both will take part and you can get some interesting properties. So we have taken the 9,10 diphenyl anthracene core, which is connected by this kind of alkyl amide chain. You have the terpyridine moiety. So for this white light emission, you have the 3 different color. You can blue, green, and red. You can get the white light. So our approach is that how rationally you can design. So now I have the low molecular gelator. Through this, it has that blue light. It is for blue emission, and it is the one-dimensional fibril, which have the diameter about 40 to 50 nanometers, and it's like that you can see that how it is in the TM image. It's called a long fiber. So this has that from the PXRD and IR, how it forms this one-dimensional. So through this, the core, I have the anthracene core. It forms the one-dimensional fibril. This one-dimensional fibril can again form interdigitation and form the 3-dimensional, where it forms where the solvent molecules enter and it forms the gel. Okay, so now if you now put the terbium or europium, lanthanide's metal ion, the lanthanide metal ions has the weak absorption coefficient, but they are low emission. So you have to introduce something which can transfer the energy to the high excited state of the lanthanides to get that emission back. So here we have taken, when you take the terbium, you can get the green, and where you have the europium, you can get the red. So now this you can see also the morphology changes. It is forming the coiling happens, and this coiling happens because of that your orthogonal orientation of the 2 terpyridine moiety. So the terpyridines cannot bind because of the steric, it will bind like this, and because of this it's coiled. Fine. So now I show the processability. You can coat in the large area, okay? But you can see one interesting thing here, that the L, which is the core of that lanthanide emission remain. So this energy transfer happened from your terpyridine part, and corresponding red and green emission you are seeing. So then we thought, if we can mix the terbium and europium, you can further tune the emission of this material. So what we did, we can tell 1:1. When you put terbium and europium in the gelation, we can get this kind of yellow emission, but when 1:1.2 terbium and europium you put, that time you can get the clear white light emission from this. Okay, this is because you have like this blue part, and it is the terbium, you are getting the green part, and from the europium you are getting the red part. So blue, red, and green, you can get the white light from this. So this is the chromatocity, and this is your quantum efficiency, and that you can, because the processability, you can coat on the blue LED, you can get some kind of white lighting LED of this kind of material. Okay, so this is the one part. So whether this kind of material you can use as the photocatalyst. Okay, so I'm not going details why it is so important, photocatalyst, that if you generate or split the water to get the hydrogen from such systems, which can use the ideal fuel for the future, or you can do the CO2 reduction to generate the fuel. So you can mitigate both the things. You can decrease the CO2 concentration in the atmosphere, or you can also get the fuel out of the system. So these things, so whatever that I am adding my core there, and core can be the photosensitizer, or it is the light harvesting energy. So when you connect to the metal ion, your metal ion can be acts as a catalyst, or you can also put the co-catalyst to the system, and you can get the co-localized to the system, and you can get such kind of catalytic activity. So why the advantage in the gel system? So it will have the higher dispersion in the solvent. Okay, you don't need huge amount of the solvent. Efficient diffusion of the charge carrier. So when you shine the light, it forms the electron and hole. So this electron and hole scavenger you have to use, and the electron, if you have the co-localized to the very close, that the diffusion path length of the electron you can decrease, and then you can use to the catalytic center. You can structural tunability, and you have the surface area. Note, you have the inherent surface area, as well as because of the nanomaterial, you can get the surface area from them as well. So this is that co-localized. I'm not going into details. That you have the incident light. That energy of the incident light has to be higher than the band gap of the material. Then you can get this electrons and hole. Then you can hole scavenger. And the excited of the electron, or the lifetime of the system, has to be higher to connect with to go to the catalytic sites to do the reduction process. So particularly the CO2 reduction, one point I want to highlight here, that CO2 reduction, it can give the different fuel. Okay, so particularly if you CO, you can get the 2 electron reduction. If the proton couple reduction in the photocatalysis happens, that reduction potential at NH at pH 7 versus standard hydrogen electrode is minus 0.43. But if you want to get the CH4, the reduction potential is only minus 0.24. Which thermodynamically, to produce CH4 is facile. But you see the number of electrons involved. Here you have the 8 electron transfer process, and here is the 2 electron transfer process. So the kinetics of the reaction is become complex because the CO, that bond energy is 750 kilojoule per mole. So that's why here is the challenge, how to get that CH4 from the CO2. So you can get directly fuel by the reduction. So there are different type of materials. It is all this huge amount of research is going on, already started 1972. They have a different type of material. So each material, there are several advantages and disadvantages. There are the hybrid material, but in the soft processable material yet to be studied in such field. So there are very high impact journal research how to, if you can convert CO2 to the CH4, all this some nature to the nature energy and different types of different type of material it appears. So this is the paper which struck our mind that if you have this is the organogel, perilene diimide. So then you have this connected with this oxo group and you have the sodium plus. So this forms the tape-like a morphology. Then they put the co-catalyst, and this co-catalyst used as the proton reduction, and they can get good amount of the turnover number for water splitting to get the hydrogen. So this came in the nature chemistry. So then we thought, how we can design such kind of low molecular gelator and connect with the different type of metal ion, and you can get some kind of different, like whether it is possible to get that hydrogen evolution or CO2 reduction. So this is first, we have this design principle. We have taken the porphyrin core. It is well researched, well studied also. It has the high absorption coefficient in the visible region. So it can form that you have the large pi core, which can form the pi-pi stacking, and which will be good for that your exciton mobility or the charge separation. So this we have taken. So this we thought that if we connect with the different metal ion, so then we can tune such kind of photocatalytic activity of the system. So this is from the gel in the DMSO water medium. You can see the visible light. This is the solid band and the 4 Q bands, and it forms this kind of gel, like that 2-dimensional layered structures. These layers are stacked together, and then we add ruthenium system. Okay, ruthenium is well studied. So it is just like one model compound we have taken. So ruthenium, you have like the MLCT, metal to ligand charge transfer, which comes around the 453 nanometers. So when you connect, so now you have the porphyrin, which can act as the light harvesting agent, and this excited electrons comes to the ruthenium, which can use the catalytic, which can do the catalytic activity. Okay, so this we have done for this DMSO, and that you have joined the titration, it can come, and when you do the ruthenium, it also forms the gel. So the seed kind of morphology, it is the time-dependent FeSM, and slowly, because of the orthogonal binding to the ruthenium center, it's just started roll up and forms like the nanotubular morphology. And here the band gap, the ruthenium, the porphyrin gel, the band gap is around 3 electron volt, and each the band gap changes to 2.33 electron volt. So there is a change also the packing diagram. That's why the morphology changes. And this is our setup. This is the 290 watt xenon lamp, and we have used the filter to get only the visible light, because around 45% of the sun's energy comes from the visible light. And you have collected the gas, and you can analyze in the GC. So first we have done in the different sacrificial agent, and particularly you can see this very active. When I did not use any catalyst, that amount of hydrogens is around 2,500 micromole per gram, and it is highly stable. And we have done the control experiment, different time interval. You can see there is no problem in the stability or the recyclability of the material. Then we use the iron dihydrogenase. So we have taken that in nature, the iron dihydrogenase used for the oxidation reduction of the proton. The similar kind of one small compound we have prepared, which is the diiron, which is the iron in the -1 oxidation state. So this we have immobilized during the gelation, and you can see from the FeSM, this iron is throughout the matrix. So then the band gap also changes from 2.344 to 1.89 electron volt, and then we have performed. So this is huge change. Okay, so we got around 120 millimole per gram of hydrogen evolution at around 12 hours. So now this is the turnover number is very high, 270 in this case, And then we thought whether we can just do into the sunlight. Yes, we can do the sunlight. So then we put this our just the laboratory top, and 1 week we have studied from 17th April to the 25th April. 1 week we have done. So we have seen that because the 10 to 4, the sunlight intensity was good. We have studied and we've seen that when your cloudy weather, that time that your proton and hydrogen evolution is less compared to highest we got in the 17th of April, and which is 160 turnover number, because you can do only for 6 to 8 hours. That's why the turnover number is less. Okay. So this we have done then calculation that how from the Mott-Schottky plot, what is the value of the conduction band, and conduction band you have that minus 0.91, and which can able to reduce the water to hydrogen. And also we have done that photocurrent measurement. You can see when there is no ruthenium and when the porphyrin, that is that your photocurrent almost more than twice that increases. Means that your excited state electrons can go easily to the ruthenium center. Okay, so then we have, this is that I am not going details, theoretical parameters that it can possible, there is electron transfer from the ruthenium, from the porphyrin to the ruthenium to that your catalytic site. So then we thought that the CO2 reduction reaction. So when you do with the CO2 reduction with the sacrificial agent as a triethylamine, at time you can get only the CO, around 98% selectivity of the CO. It's very important that you have multiple products you can get by the CO2 reduction, but you have to get the highly selective, but CO. But surprisingly, when we change the sacrificial agent, that benzyl 1 to do 1,4-dihydronicotinamide, that is called the BNACH. Okay, this BNACH is give that you can get the CH4. Okay, with the turnover number 204. It is quite significant. You can CO2 to CH4 because it is the 2 electron donor BNACH, and it is also simultaneously give to the proton to the system. So proton couple electron transfer and triethylamine will supply the electrons. So you can get selectively to the CH4. So next 2.5 minutes, whatever I have. So I have taken this is the low molecular weight gelator. You have the design. So now if you have the discrete metal complex which can be used for that the gelator, and you can self-assembly with the different kind of binder, you can and propagate the hydrogen bonding interaction 3-dimensional where the solvent molecules entrap, and you can get some kind of unique properties. So before that, just we can change the metal ion in the porphyrin systems, then you can do some many other things which I am not going details. So this thing that I just, it is the tail of metal organic polyhedra, but it is just a simple starting this reaction how you can get. So you have discrete molecular complex, it is the molecular square connected with the gallium, and you have this kind of organic molecules and surrounding by the oxygen. So this is the negative charge, and you have the NH4 cations and form the 3-dimensional structure. Interestingly, this when you put in the water, it's soluble, and my complex remain intact in the solution. Okay, this that solution happens because you know when any salt dissolve, so that the solvation energy that your crystal solvation energy higher to that your crystal energy of the system. So that it is dissolved. So then we put that if you take the ammonia, which has that your oxygen group, and it's through the hydrogen bonding, it can capability to forms the gel. So we have put some amount of the ammonia we added, and you can see there is the formation of the gel, and this is the beautiful tube-like morphology it forms. Okay, and the rheological study that it showed the viscoelastic nature of the material, and you have this kind of nanotube. So then we have done the surface, what is the charge of these things. The zeta potential measurements suggests that is the minus 22 millivolt, it is the surface charge is negative. So now I have the one-dimensional aligned nanotube and surface charge is negative, and which is the pH responsive. Okay, so now the initial pH, because of the presence of the ammonia, it is 11. Now you add few drops of acid, pH 4, that it will just form the precipitate. Again you change, so you can reuse it. So this aligned nanotube, first we, for the better visual demonstration, we put the cationic dye and then anionic dye and the deuterionic dye. Cationic dye, it is almost completely trapped. This is by the gel matrix. But if you anionic dye, sulfurodamine G, it cannot go in. So because electrostatic repulsion, it can go out from the system. So then we have the deuterionic, because both of the things only certain amount it goes. So then we thought whether it is possible to separate this kind of two mixture of these things. And then we have taken this two dye mixture, one cationic and anionic. Sulfurodamine G, it can easily pass through, but then later on you can come the Nile blue and you can get this kind of separation from the two mixture. Not only dye, you can get such kind of soft, weak kind of interactions of the different kind of metal ion. One metal ion can go out, one metal ion you can capture into the system. Okay, so I'm not going, so you can also put the tri-component material like this and you can get the tunable emission, even including that you can get the white light of this system. Okay, certain kind of you can get, and you can show the high processability of this kind of system. Not only that, you can connect this kind of discrete molecules, intercalate between the two-dimensional graphene sheet, and you can get this the graphene gel, which you can use for the supercapacitor and other application. And not only that, two-dimensional nanocalay also you can intercalate, and you can see this, and you can get the high adsorption behavior. You can introduce the mesoporosity. And beautiful ordering, you can see that how it is intercalated between the graphene or the nanoclay. So this is the summary. Whatever I shows that you have these low molecular gelators, and introducing the metal ion, you can get some kind of new properties into the systems like photocatalytic application to get the hydrogen or carbon dioxide reduction, tunable emissions, or you have new kind of gelators which can be, you can separate based on the charge particle of this. And finally, I would like to acknowledge my students and different funding agency, and thanks for your attention.
Thank you.